Proszę Państwa, dotarliśmy do momentu, kiedy możemy przedstawić ostatniego, niestety dzisiaj, prelegenta. Profesor Józef Pieprzyk będzie mówił o multi-party computation via graph coloring, ale najpierw poproszę profesora Michała Karońskiego o przedstawienie sylwetki naszego gościa.
Dzień dobry Państwu. Jest mi niezmiernie miło i z ogromną przyjemnością chcę przedstawić naszego kolejnego wykładowcę, pana profesora Józefa Pieprzyka, obecnie w Macquarie University z Sydney. Chciałem bardzo krótko opowiedzieć o pewnej fakcie biograficznym łączącym się z poznańskimi kryptologami. Państwo pewnie się orientujecie, pan Marian Rejewski pochodzi z Bydgoszczy i to jest właśnie fakt, który łączy profesora Pieprzyka z Marianem Rejewskim. Jest również z Bydgoszczy. Bydgoszcz jest niezwykle dumna z tego faktu i myślę, że ma rację, ponieważ profesor Pieprzyk jest czołowym kryptologiem w skali światowej. Na jego osiągnięcia składa się bardzo dużo publikacji. To jest ponad 160 publikacji i ponad 5 podręczników książek. Jest redaktorem kilku czasopism, może ja wymienię przynajmniej niektóre z nich, takie jak International Journal of Information Security, wydawanego przez Springera, jak również Journal of Mathematical Cryptology. Profesor Pieprzyk ma bardzo szerokie zainteresowania, jeżeli chodzi o kryptografię, kryptologię. Sądzę, że do głównych dziedzin jego zainteresowań, chociaż lista, jeżeli spojrzycie Państwo na stronę, jest bardzo długa i nie mógłbym jej wyczerpać, ale zbierając w pewne grupy dziedzin, chcę powiedzieć, że zajmuje się bezpieczeństwem sieci komputerowych, bezpieczeństwem danych, projektowaniem i analizą algorytmów kryptograficznych, analizą algebraiczną szyfrów blokowych i strumieniowych, teorią protokołów kryptograficznych, schematu podziału sekretu, ochroną praw autorskim, bezpieczeństwa i biznesu i wielu dziedzin pokrewnych. Niestety nie mogę powiedzieć o panu profesorze Pieprzyku, że jest absolwentem Uniwersytetu Adama Mickiewicza, ponieważ jest absolwentem Uniwersytetu Mikołaja Kopernika i no, to jest pewien rys na karierze profesora Pieprzyka. Proszę bardzo, będzie nam miło posłuchać wykładu.
Dziękuję pięknie za zaproszenie i tutaj dziękuję władzom uczelni i wydziałowi i Zakładowi Matematyki Dyskretnej, a szczególnie tutaj profesorowi Jerzemu Jaworskiemu. Bardzo mi było miło tutaj się wyrwać z słonecznej i ciepłej Australii i troszkę się ochłodzić. Także chciałem też przy okazji wprowadzenia podziękować profesorowi Korońskiemu za miłe wprowadzenie i tak mi się przypomina taki fakt, bo też miałem okazję przedstawiać profesora Ariana Lengstre na konferencji, miał tak zwany zaproszony talk. No i właśnie mówię, no to profesor Arian Lengstre właśnie to jest bardzo wybitny matematyk. To jest właśnie ta pierwsza literka L z bardzo znanego algorytmu LLL w kratach. No i właśnie nie oczekiwałem takiej reakcji, bo potem profesor Arian mi podziękował, ale powiedział, bardzo mi przykro, ale ten algorytm, który mówią Lengstra-Lowasz, właściwie powinien się nazywać Lowasz. I proszę mnie nie imputować, że ja jestem tym pierwszym L. Więc potem się śmiejemy od czasu do czasu na naszych wewnętrznych seminariach. I właśnie ostatnio Igor Szpaliński, jak przedstawiał właśnie jakąś tam teorię matematyczną, i właśnie mówi, no to właśnie będziemy stosować algorytm Lowasz. Także to już się przyjął u nas jako taka dykteryjka. Chciałem Państwu dzisiaj przedstawić taką dosyć świeżą pracę, którą myśmy zrobili w zeszłym roku, chociaż nad tym problemem myśmy pracowali przez chyba 3 czy 4 lata. Mimo że Państwo zobaczą, że to jest dosyć prosta konstrukcja, jednak okazało się, że myśmy mieli sporo kłopotu, żeby sobie jakoś wytłumaczyć, jak ten problem rozwiązać. Ja może przejdę na angielski, dlatego że właściwie wszystkie slajdy mam tutaj po angielsku, więc to jest tytuł, a tutaj może taka fotografia, na której Państwo znajdziecie właśnie tych współautorów, więc zupełnie po lewej stronie na dolnym rzędzie jest Ivo Desmet. Zresztą jeżeli Państwo jesteście ciekawi, to jest to zapalony tancerz. Jeżeli pójdziecie na YouTube i wpiszecie Dancing Professor, to właśnie on tam wyskoczy i będziecie mogli podziwiać jego talenty tancerskie. No, mnie to raczej nie potrzeba identyfikować. Po mojej lewej stronie jest Hua Zhang, a tuż nade mną od prawej strony licząc drugi jest Ron Steinfeld. And now I can probably jump to the outline of the presentation, and I will first give you a motivation and definition of what is multi-party computation, and gives you some sort of examples. I was now a little bit well, shy to go into some more practical applications after Andrew's talk, in which the human factor always goes in. But also I will define our problem. In this problem would be definition, attack model, and some previous approaches. And discussion of our results. So early constructions, that's the part which you don't find in our paper at Crypto, because it was the part in which we struggled and we really couldn't find working solution. Then some negative result, which is probably quite obvious. After presentation will be hopefully obvious. And then our black box protocol construction methodology. And we will apply 3 steps in those constructions. Reduction from general problem of finding product of n elements, using a subprotocol which only does this for product of 2 elements, and then we show that this subprotocol can be nicely represented by problem. We define this as a T-reliable planar graph coloring. We simply don't know whether or not this graph problem is or maybe not related to some well-known problem in graph theory. Or maybe there's some sort of connection with combinatorics. I don't know. Maybe some of you will have a look. And then I will actually give you the construction of T-reliable planar graph coloring, which is deterministic and unfortunately not efficient. In general, if you would like to apply this for arbitrary n, then the size of the graph grows exponentially. So it's a very nice result, but not very practical. But hopefully I will also give you a probabilistic coloring, which is, on the other hand, very efficient. So it's polynomial. And unfortunately, we have to pay a price for this one. The price is that this graph may not be T-secure or T-private with some probability. But the probability can be made as small as we wish, and then the size of the graph will grow. And obviously the conclusions and open problem. I probably will not go into technical details about probabilistic coloring, and probably you can expect that I will skip some of the slides at the very end. What is MPC? So multi-party computations is a protocol in which you have n independent parties and a function f which at this stage could be of arbitrary form. And then each party has its private input. So party Pi has a private input Xi, and we would like to design a protocol with only parties P1 to Pn, with no trusted authorities, with no external interference by some other trusted parties, to compute the function f. But in such a way that after the execution of the protocol, the parties will still preserve the privacy of their own inputs, xi for Pi, and they will only know the result of the evaluation of the function f. And obviously, because after broadcasting the final result, the parties will have some perhaps additional information which could be inferred from private input and discovered value of the function f. And you can only infer from these two pieces of information and nothing else. That's precisely the definition. And we would like to design some sort of network. So we would like to find a network in which you have a lot of parties inside, and they will interact with each other in such a way that after interaction they will be able to discover the value of the function for the private inputs. Now, security of multi-party computations could be, well, considered in two different cases. So we could consider passive attackers. They called honest but curious. It means that we assume that any party in the protocol will follow honestly the protocol without any mistake. What we assume that they may be wishing to discover some extra information about some other party's input. But an important assumption is that they will follow the protocol. And there is also another, a little bit more complicated case, when you assume that you have active attackers, and in this case, you don't assume that they will follow the protocol. The only assumption, a probably reasonable one, would be that they will start from some a private input xi at the very beginning. They probably commit themselves to this input, and later on they will have to consistently use the same input. They must not change their own private input inside the execution of the protocol, otherwise they will be detected. But we will not, I will not discuss this case. We still don't know how to solve this. And two generic types of security, and in cryptography you have two types. Computationally unbounded, so information theoretical or unconditionally secure. And the second one is computationally bounded or conditionally secure. And our solution is the first one. So we don't rely on any computational assumption or factorization or whatever. It's just the attacker can be infinitely powerful, and to crack the system, he has to guess. And this is the assumption. Well, application of MPC. So you can actually see if you are a little bit biased towards MPC, you can see almost most of the cryptography as an instance of MPC. But let me start from the beginning, because Andrew Yao, a lot of cryptographers are Andrews, so I don't know, maybe that's the some feature which distinguishes good cryptographers. So Andrew Yao defined in 1982 a millionaire problem. So he assumed that there are two very rich people, typically Alice and Bob, and they would like to get together exchange some information and find out who is richer. But they will not try to release the information about the exact wealth of each of them. So, well, it looks like a very interesting problem. It was actually a lot of solutions. Later, you can actually find that, at least from theoretical point of view, there is a generalization of Yao's problem called two-party vector dominance. In this case, you would like to compare vectors, but we know that sometimes comparison fails because you don't have a good or well-defined order for vectors. But you would like to get a result if each coordinates of those two vectors are dominated by one of them. So, for example, consistently. And then obviously this result should be generated, but if these two vectors cannot be compared, then protocol should generate some answer to the party indicating this is the case. Also, more and more, there is an area of cryptography in which you would like to compute some set operations privately. It can be applied for some, for example, databases, let's say in two different companies, like, let's say, GP and hospital. By law, they are forced not to release the information about their patients, but they may try to find out some interesting information for statistical purposes and find some intersections of different cases. And that's precisely what two-party computation of set operation they do. Also, there's a private information retrieval, also growing application for the following scenario, that a company would like to outsource the database to some outside company which specializes with database maintenance because of savings. And then obviously, when they retrieve the information, they would like to do this in such a way that the database, which is in untrusted environment by the provider, this interaction will be hidden. The provider will have no information about which information the owner takes from the database and which stores and so on. So this is also can be seen as a multi-party computation, and probably also electronic elections. So in a sense, you can actually treat the result of election as a function. And then each voter casts this private X, and after finishing the elections, you would like to reveal to everybody what is the evaluation of the function f. Well, this probably I should actually skip, because there's a recollection of what is the algebraic group. Oh, so this is Goana. Problem setting. A lot of multi-party computations and protocols are already known for abelian groups. We concentrate on non-abelian groups. So the problem we try to attack is to find the product of elements which are private inputs. So we would like to evaluate function fg, where the inputs are x1 to xn, and the result is just the multiplication of the private elements, x1 multiplied by x2, and so on, xn. Multiplication is for non-abelian group, like multiplication of matrices. So you cannot commute the elements. And what we would like to have, so we have the very well-defined input. They should be private. Output is obviously requested to be the product, and we would like to also have a T privacy. So we assume that our attackers follow the protocol, but they would like to get some additional information. And we would like, in this case, have a T privacy, so we would like to design a protocol which will be secure against a collusion of T parties. T or less, obviously, not more. And the title was Black Box. I mean, the title, I'm using the black box construction. It is an abbreviation for the restriction that our computations within the protocol are only group operation, multiplication, the inversion, because it's defined in the group, and additionally random sampling. So we have access to truly random generator, which gives us elements from the group. And that's the only what we want and need. This is some sort of summary what has been done so far. And you can see that there is already well-known algorithm for efficient black box protocol for abelian groups. And the brief sketch of this protocol, you can actually see what happens. So if we assume that we have here 4 parties, right? So at the very top of this graph, we have yellow, which is party 1, red, party 2, blue 3, and green 4. And those parties at the very beginning, they have their own private inputs, x1, 2, 3, and 4. And now what they do, for their private input, they create 4 shares of the private input using the 4 out of 4 secret sharing scheme. And you can see this yellow guy at the very top distributes the shares to the parties in the second row. And this is executed in the same way for second, third, and fourth. And in the row of share multiplication, the parties, so the color indicates which one is which, takes the shares received from others and multiplies them. And then sends to one selected, in this case P1. So in the second row, all these guys are multiplying the shares and sending to the yellow at the very bottom. And you can very quickly, by very elementary computations, convince yourself that the result at the very end is the product of those 4 elements. This works because we have abelian group. So you can see that in which, so you can see that this actually works very well. The other thing is the last guy, the yellow one, after getting the final results, he or she broadcasts to everybody. So everybody knows the final result. So this is what has been done, and this is the very well-known protocol. There are some other constructions, and the first one is generic non-black box. Well, non-black box because the designers are using some extra operations. More specifically, they actually are building some protocol using combination of AND and NOT Boolean circuits, which is obviously not part of the abelian group, so it's outside. But you can do it. They also use some Shami scheme to reshare the private input in secure way. And also there is another construction based on the ring. In this case, the construction allows the owner of the non-abelian group to inject this to ring and then run the protocol. In both cases, those protocols are not really optimized. and are using some extra operations which are not really defined in non-abelian group, and we don't really like this. So our goal is to extend this black box abelian group protocol to non-abelian groups, and also avoid threshold sharing, because threshold sharing is a little bit more complicated. We will be using only k out of k sharing, which obviously preserves high efficiency. Right, also because of non-abelian group, we will try to model our interactions as a graph. But because of non-abelian, we have to stick with the planar communication graphs. Planar, it means that you cannot swap arguments, because in abelian group swapping is not allowed without the consequence to the output. So, and this is our negative result, which says that if we have a protocol with n parties, then there is no n divided by 2 ceiling private protocol for computing the function. This probably is not really obvious for you, but will probably be obvious when I will give you an example. Because for the example, you will see that some of the constructions are not really possible. So I will skip this. And then I will tell you what we have done in terms of early construction. So the first idea was to design some sort of graph which will allow participants to compute the product for non-abelian group. And we also assumed that each party can generate their own random integer r, small r, I. And also we allow that each pair of parties is able to establish a joint or common secret, like R12. It means that this secret is known by party 1 and 2. And you can see that for the very simple case, n is equal 3, t is equal 1. So according to our negative results, t must not be bigger than 1. Then you can see on the graph the interaction. So the 1 is party 1, has a private input x1, 2 has x2, 3 x3, and then party 1 takes private input x1, generate its own random number r1, multiplies this from the left-hand side, and also uses the secret known between 1 and 2 and multiplies this from the right-hand side. And send this to party 3. And now you can see 2 does something equivalent. It takes R12 inverse and then puts x2 and the R23, so the element which is known between party 2 and 3. And those 2 elements are sent to party 3. Party 3 multiplies those 2. You can see in the middle, R12 disappears. And as a result, party 3 knows R1, X1, X2, R23. And party 3 sends R23 inverse, multiplies by X3 to the party 1. If you see that party 1, if party 1 multiplies the inputs, then it gets R1, X1, 2, 3, and then strips off R1 because party 1 knows R1 and gets the result and broadcasts to the rest of the parties. Well, that's fine. Looks like it may actually work. So now we have to evaluate the security. Well, so we have to actually consider 3 scenarios when the attacker this dishonest, but curious party is trying to learn a little bit more than it should. And we actually have 3 cases when this attacker is P1 or P2 or P3. And for the example, we assume only that the attacker is P1. And now we create a view for the party P1. So all the information P1 knows by definition, because it knows the private inputs on random elements shared between one and the rest, and also something which is learned during the execution of the protocol. And you can see that private elements x1, r1, r12 is known to P1, and also the element r1, x1, x2, r23, this was observed during the execution of the protocol. And important, after the execution of the protocol, P1 also knows the product, x1, x2, x3. Because x1 also knows P1 also knows x1. So if the party knows the product and its own private element, that obviously knows the x2, x3. But can P1 learn more? And the answer is no. Well, you can write how many relations you have and how many unknowns you are dealing with. And you can very quickly come to the conclusion that P1 learns nothing. And then can be proved for P2 and P3 in very similar way. Well, so we actually went to the case n is equal 5 and t is equal 2. All right, so this is actually the first one which is really non-trivial. And then you can see that party 1 takes private input x1 and puts the secret element r1, 5, so the element which is shared between party 1 and 5, its own r1 and also r1, 2. And r2 does something equivalent, r1, 2 inverse, x2 and the random number r2, 3 multiplies and gets obviously cancellation of the left and right element of r1, 2, and this is result which is probably, okay, so this is the result which you can see, and obviously these two guys will prepare also this kind of information with the random element which is shared between 3 and 4, inverse x4, r4, 5, and here is very similar. This is obviously sent to 2, 2 multiplies those 2 and gets this one, the cancellation of those middle elements, r4, 5, and its inverse is obvious. And you can see that for the party 5 gets this information and also the information prepared by party 3. And if those two elements are multiplied, then obviously these elements get cancelled, and this is the result. And those two, if you multiply, you will get obviously the product of 5 with R1, but R1 can be stripped off by party 1. And that's the result. And in this case, we actually consider also the security. This time, analysis is a little bit more complicated because you have to consider 5 choose 2 possible scenarios of attacks. And we only consider this scenario when you have P1 and P3. I'm just looking at my watch. And you can very quickly establish the view, what information is known to the pair, P1 and P5. And you can see this is obviously known because this is precisely the pairs they know. And also the observation from the run of the protocol. So you take every information which is seen by party 1 and 5. And after a simple analysis, you can see that actually the information they have, extra information, can be summarized by these 3 points. And this another 3 are just derived from these 3 independent. And you can see that you have 3 relations, 5 unknowns. You cannot find the private inputs. And this actually guarantees that this structure is secure, at least for this particular collusion of parties. Right, and we actually couldn't find construction for 7. N is equal 7. We tried many times. Eve was also coming with some sort of, oh, this time I have it. Oh, well, it didn't work. Because we have to check for 7, choose 3 possible attacking scenarios, which is 35. So it becomes a little bit tedious, and we finally gave up. And this is our final construction, which in a sense summarizes our disappointment, because we actually gave up trying to find a product of n elements in one go. You can see that actually the first step we apply is actually implementing a sequence of sub-protocols. So take a look at this picture. So what we are trying to do is to find a sub-protocol, like this one, which will be used to find in T private way a product of 2 elements. So in this case, we will go first x1, x2, then this result is here, and multiply by 3, and so on. So at the very end, we get the requested product of n elements. So our task now is to design a sub-protocol for multiplications only of 2 private elements. So, well, this looks like a little bit simpler. And we hoped that this will work. But obviously, this sub-protocol has to be designed in a very specific way. First one, that private input could be of any other party. So this private input has to be given to the sub-protocol as the collection of shares. At least as many shares as T plus 1. Cannot be less. So in a sense, this is the input, which is in the form of shares of input X and shares of input Y. And the output will reveal the product, but in the distributed way. You don't get the result of those 2 input X multiplied by Y in single wire. You just get T, at least T plus 1 outputs, which actually define shares of the output. That's the very important point. Well, this is some technical requirement that we would like to so-called strong T privacy, which is defined that for each case, the input shares will have at least one input which is not visible to the collusion of attackers. And the same with Y, and the same with the output, which is another way of saying with this, the sharing restrictions. And then we proved that having this slanted linear tree, we could actually run T-private protocol for arbitrary number of elements and parties. And this is the second step, implementation of 2-product subprotocol. And you can see the idea. At the left-hand side, you can see, okay. So here you can see the inputs of the shares of X, input X, and on the other side here, Y. And this is the output. We have a grid, quite regular grid of nodes, and each node is assigned a party or color. And what given node or party does is that collects. So see, for example, this green guy, it takes inputs from the neighbors, from the top. After getting the elements from the neighbors from the top, it multiplies and sends to the neighbors down by using the secret sharing, so resharing the result. And this is done consistently throughout the graph. At the very end, the result follows. Now we discovered that if we would like to have a T reliable, so secure against the collusion of T parties, coloring, then we have to have something like collusion avoiding a path from input X from Y to the output. In other words, if this input is not in the view of the collusion, so collusion parties don't see this, then this collection of, hopefully this or maybe other, there is a path which gives the path outside the view of the collusion party to the output, and this has to be present for X and for Y. Let's say, see, so let's assume that this path and this path are not in the view of the collusion party. Then this protocol will be secure. Will not be enough information to derive any extra data. This is the lemma, which can be a little bit technical. I will skip this. And now step 3. So we were able to give a construction, deterministic construction, which can be implemented as this kind of graph, which has L rows and L columns. Oh, that's right. So now I have, so this is the construction, deterministic construction, and now I can tell you how you can actually implement this for the very simple case when you have n equal 3 and t is equal 1. And you can have up to 3 choose 1 collusions, and those collusions are actually given here. So you have a party 1, which is dishonest. It means that 2 and 3 is honest. 2, it means that 1 and 3 is honest. 3, and 1 and 2 is honest. And the same here. And you can see that if you would like to get a secure path from left-hand side to the right for specific collusion, you need to only select for these entries the elements which are intersection of the row 1 and column 1. You have a 2 and 3. For row 1 and column 2, you have 3 and 2. And if you fill up this table in this way, and later on choose some of the vertices which are allowed according to this table, then you will get something like this one. So this is the very simple graph, which for the input X and Y, which are distributed using 2 shares, are going through to the output. And now we can actually see the first scenario when you have P1 is an attacker. So an attacker is here. And we would like to have two paths from X and Y to the output, which are avoiding so this shares or information is not in the view of the attacker P1. And you can see, you can find one share at the top goes here, and X goes here, and they are joined together by 2. And on the output, you have a result which is not really visible, a part of it is not visible by 1, so it's secure. Well, if we have party 2, then you can see that those two vertices, 2 and 2, are under the control of the attacker, and these two paths from X to the output are drawn here. So from X you can travel this way, and for Y you can travel in this way. So it is secure, and also for the case when you have the third compromised. And then you can generalize this for n is equal 5 and t is equal 2. Well, this is actually quite a feat, because if you would like to do it, it's quite complicated and time-consuming. But the graph you can get is this one. And you can now see that because you have a t is equal 2, so from the input x, you have to have at least 3 shares. And from y, also 3 shares. And to the output, you have to have at least 3. In this case, you have 4, which is fine. And now if you would like to analyze whether or not this is secure, then you have to convince yourself that for each particular pattern of collusion, you will find this collusion-avoiding path from X and Y to the output. And this is the example of if the attacker is P1 and P2. And you see, you can find for X and for Y. They avoid none of these paths is visible to the attackers. Well, if you take P3 and P5, well, that's another path. And you can run through all possible, and if you get this collusion-avoiding paths, it means that, according to our theorem, this is actually T secure. And we can actually very quickly prove that this construction is not very efficient, because the number of rows and columns in this construction is proportional to n over t. T is roughly n minus 1 divided by 2. So for this particular case, this grows exponentially. It's smaller than 2 to the n, but still the growth is equivalent to this one, asymptotically. And what we considered, hopefully you don't sleep like this koala. And we considered also a little bit simpler construction, but probabilistic. And what was the idea? So we used a little bit bigger and more richer in terms of edges graph. And we draw the nodes, and then for each node, we toss a coin. And we select randomly and uniformly for each node one of n parties. And we assign those colors or parties to each node. And then we ask ourselves a question. Well, whether or not this graph will always give us a collusion-avoiding path from left and top side, so we always have the path from X and Y to the output. And it turns out that we proved that we can do it. And if you would like to get appropriate probability, do I have on this one? Then you have, that's the another. Okay, so here is the, so if we would like to design a graph for n parties and get probability of T not being, the protocol not be T secure or T private, then we need to select big enough graph. So L is the number of rows or columns in the construction, and this is equivalent to this one. But you can see that you can actually go for arbitrary small gamma, to get a construction will be almost guaranteed with small probability of mistake. And most of the time, we actually can live with this kind of mistakes. For instance, for RSA, if you test the primarity, you always use some probabilistic algorithm. And if the probability of making mistake is 2 to the minus 100, then you can live with this kind of probability. And, well, that's probably it for today, except that this is actually one of the beautiful flowers of Australia called Waratah. And this is the conclusion is open problems. So what is the important lessons we learn? That, well, graphs could be quite interesting and useful for this kind of computations. Mind you that our protocol will also work for abelian. It's a little bit strange, but you can do it because this is actually quite natural. The open problems we are looking at is whether or not we can get a deterministic and polynomial construction. So our deterministic is exponential, so it's not very efficient. For this particular problem, we think, after some investigation, that this may not be possible. Maybe sub-exponential may be good, but I don't know. We don't know at the moment. Another problem which is related to this setting is whether or not there are some connections between the problem of, in graph theory we defined, and some already known problems in graph theory. And we actually were looking through, but we couldn't find any appropriate. Maybe this kind of structure could be hidden inside of some sort of combinatorial design we are not aware of. If you can, for instance, see something which has some sort of relation to our construction, I would be quite happy to hear from you. And that's probably enough for today with all this hassles with the presentation. Thank you very much for your attention. No właśnie, bo ja tu reprezentuję tak zwany, jak to było? Południową półkulę. Dziękuję bardzo, to jest bardzo miło.
Podziękujmy w takim razie wszystkim naszym kolegom.